This is video, now I can't even remember, video 6 I believe. Video 6 in the Math 120 COVID isolation scenario. So we're going to keep it rolling. What we're going to do is linear transformations. There will be probably 1 or 2 more videos about standard matrices of linear transformations, and then it depends on where I get and how far we get. Basically, what do we have left? We have linear transformations. In that scenario, I'm going to give the definition of linear transformations, and then we'll do a couple examples of whether it is a linear transformation or it's not a linear transformation. Then we're going to show that every linear transformation has a standard matrix, and every matrix can define a linear transformation, so they're essentially the same things. And then what we're going to do is talk about composition of linear transformations, and then we're going to give a demographic of linear operators moving things around in 2 space. Probably for this semester, because of the way it's gone, we'll probably stop there at 2 space, but usually I give a demographic of 2 and 3 space, how to move things around in 2 space and 3 space, and then how to compose those types of things. And that'll be 2 or 3 more videos. We may do a little bit about eigenvalues and eigenvectors, just because that's the bee's knees, and that's the whole point of why you should be taking linear algebra. And if you're taking more, eigenvalues and eigenvectors are the most important part of what you want from this type of class. So I'll talk about it a little bit. It won't be on the final exam, don't worry. The cutoff is linear transformations. Here we go. Definition. Again, I'm going to assume a little bit that you have basically the idea of what a function is, but I'll define what a transformation is quickly first, and then what a linear transformation is, the guys that we want and why are they linear. So a transformation T from Rn to Rm is a rule, essentially, just like functions, that assigns to every vector x in the domain Rn is called, we'll draw the pictures in a second, but Rn is the domain and this Rm is the codomain, usually, classically. Don't worry, you won't have to know too much about these things. For every vector in the domain x, it assigns a unique vector y, which is t of x. We're going to write it in Rm. Our notation for that is going to be t goes from Rn to Rm, and then we write this just like functions. We're going to say that we take a point x in here and it gets mapped to t of x, which we're going to call y, or u and v, or w and x, or doesn't matter what I call them, but this is just like functions. This is actually going to be for regular functions, and what are the regular, we can talk about them in 1 dimension because we're going to talk about operators, but who are the linear equations, and lines have linear equations in from R to R. But not all linear lines or linear equations are linear operators. Only the lines to the origin, because 0 has to map to 0 in a linear operator. So if your y equals mx plus b, that is a linear equation. But if you have a constant term, you're not a linear transformation or a linear operator, as what we're going to define this as. And this is in the codomain, we're going to call it. Notice also that T is, and this is hard at first, and especially it can get more and more abstract in other classes. If you take more, we're going to call this an arbitrary vector space V, and this an arbitrary vector space W, and then they're not even, this is going from like functions to real numbers or polynomials to some other thing, matrices, or moving things around, and we're mapping from different objects to different objects. In this case, what we're definitely doing is we're moving points in dimension 2, say, to dimensions 3 or dimension 1 or to dimension 2. You can move up in dimension or down in dimension or straight across in the same dimension. But the zeros and the vectors in here, x in here, you have to remember, has n coordinates. And the image vector in here has m coordinates. So they're different size coordinates. and they're in different dimensions sometimes. So the 0 in here is not the 0 in here, and the addition in here isn't exactly the same addition in here, and the scalar multiplication in here isn't the same in here, because they're both vector spaces of dimension n for some n, or m. That is going to be the same, but it's not quite the same scalar multiplication, because it's scalar multiplication in this dimension, and it's scalar multiplication in this dimension, or it's addition in this dimension, or it's addition in this dimension. Or in particular, the 0, I have to reference whether it's in n dimensions or it has n coordinates, is not equal to the 0 in m dimensions. And we're going to say 0 maps to 0, but that, when it's different dimensions, we're saying the 0 in 2 dimensions is being mapped to the 0 in 3 dimensions. It's not the same 0 anymore, even. For your mind, yes, eventually we'll pick n to n, and then we won't make this abstract, and it will go back to what you think, 0 maps to 0. But when we say these things, and this is why in our definition, why do we want the special ones, or what we're going to call a linear transformation? And someone already emailed me from the class saying, I like the video. I put another video for the engineers about linear transformations. Go watch that one too. It's in the list, in another playlist, in the linear algebra playlist. But if you look at this, we have what a transformation is. Why do we call them linear? What's going to happen is I have linear operations, addition and scalar multiplication in here. And I have linear operations, addition and scalar multiplication in here. And I want the transformation to respect those operations. And I want to move it to and preserve the linear operators in here and transform them linearly into this space, so that you can pull out scalars and split sums, because the sum, I'll draw it, but the sum in this side is not the sum, it's a sum in Rm. And a sum in this side is a sum in Rn. And so it's different dimensions. When they're different vector spaces, it's entirely a different addition, possibly altogether. Adding polynomials and adding matrices is not the same. It is the same. Definition. A transformation T from Rn to Rm. It is backwards. I have it backwards. It should be m to n. I'm going to do it now. Rm. I want a is going to be m by n eventually. You'll see. So it goes backwards. Rm to Rn. So a transformation from Rm to Rn is called linear if what? Some of the books have one axiom, some have two, and I'm going to do the two versions because at first it's easier to show this instead of doing it all at once, but I want to point out that this is why we call it a linear transformation, because it preserves the two linear operations. So for scalar multiplication, what that says is, one, it must spit out scalars. If k is any real number and x is any point in Rm, then it should be this anyway. I don't know what I'm thinking. Stop changing it. It's too late. I'm changing it one more time. Go back to bleep, 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 bleep. Pretend I never did it. You can edit that almost. Either way. T is a linear transformation from Rn to Rm. If I now take any scalar in R and any x in Rn, this is going to say what? What does, first of all, let's look at what kx looks like. And this is what you have to do every time we do this. So in the definition, this is going to be kx1 to kxn, scalar multiplication. And if I have that, then what it says is t of that. So this is scalar multiplication in Rn. And what that says now is, if you apply t to that and move that point, this guy, where is it going to go? It says you have to do k times t of x. But this is scalar multiplication in Rm. So that's what it's, why we want it to be linear and why it's called linear. It's respecting the linear operator of the linearity in here. If you scalar multiply in here, what this says here is, take a vector x in Rn, then I scalar multiply it, which is contractor dilated by a factor of k in Rn, and then I move it with t into Rm. That's the same thing, equals. That's the same thing as if I had not scalar multiplied x, but then taken that point in Rn, moved it through t, then scalar multiplied it in Rm. And that's what I want, and that's not always true. And that's what I want. It preserves the linearity. It's preserving the linear operation of scalar multiplication in Rn to equaling the scalar, preserving the scalar multiplication in Rm. And that's why it's called linear. And what's the other condition I need? The other condition I need is to, if x and y are in Rm, and what is that going to mean that they look like? X plus y equals x1 plus y1, coordinate-wise, xn plus yn. You have to do that every time. Every time you have to build the scalar multiplication, you have to build the addition, and you have to see what happens. Does it split it? Then what we say is t of x plus y equals t of x plus t of y. It splits sums. But remember, this is saying if I take two vectors, 2 points in n space, and I add them, then move them with t. That's the same thing as moving them individually with t, and then adding them in Rn, m. This is in Rm, and this is in Rn. And not every transformation that moves things around from one space dimension to another dimension does this. So the ones that are good for us, and which will, how do we linearly describe every vector in Rn? Through a basis with scalar multiplication of k1 times v1 plus dot 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 plus kn times vn. And then if I want to know how an operator moves every point in space can be described by these guys. And then watch what happens. T of x will be what? T of k v1 plus dot 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 plus kn vn. And what's that going to do for me? Oh ho ho. I can use these two properties. That's going to say that will be k1 t of v1 plus dot 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 plus kn t of vn. To describe where every point goes, all I need to know is where the image of the basis vectors goes. This is why it's so important. This says that to know where t moves any arbitrary point, if I have a basis, and it preserves this, all I need to know is where that operator moved the basis vectors, n guys, and I know where everybody moves under that operator. Again, that's weird to say here in rhetoric, but what that says is to know where an operator moves every point in n space, all I need to know is if I have a basis for that vector space, I can write every vector as a combination linearly with the two linear operations, scalar multiplication and addition. And if it behaves well, I know that I can get this in the image space. And therefore, it's uniquely determined by, every point is uniquely determined under this operator, under where it goes under these image vectors. Okay, so the first result we get from that is, when is t a linear transformation? It's a linear transformation. Oh, there's the one thing I also forgot, is t is a linear operator. If it goes from the same space to the same space, it's operating on Rn, it's moving stuff around. We're going to give a systematic demographic of operators from R2 to R2, how to move things around in the plane. And then we'll do it in 3 dimensions and how to move a plane in space, an airplane. Autopilot uses 3x3 matrices. Yaw, pitch, roll. What does our first result say? Now that we have this, a linear transformation or a linear operator or an arbitrary transformation is linear if it satisfies these two conditions, which you can jam into one, but we won't. So what do you have to have? You have to have that it spits out scalars and it splits sums, essentially, is what's going to happen. And then the third condition you always want is that this theorem tells me this is the best way to use the contrapositive of this statement to show that you're not a linear transformation. It says if you're a linear transformation, then 0 maps to 0. But the n-dimensional 0 vector goes to the m-dimensional 0 vector. What that really means is this: t of 0, 0, where this is n by 1, goes to 0, 0, where this is m by 1. That's what it's saying. 0 has to map to 0 in the respective dimensions. Why is that useful? I will never use this to show that something is a transformation, you need to see how we set up mathematical statements. This is A implies B. What the first thing says is A is T linear. Is how I set these up for myself at first. You have to say, and then you see what it's saying, and then you can realize, hopefully, that that's never what I'm going to use to show it's linear. It's assuming it's linear. The statement is saying, assume you've already checked it's linear somehow, which we're going to do in the next example. But that's its assumption. Its antecedent says you've already checked it's linear, so that's not how I'm going to use this statement to ever show that it's linear, because it's saying it's assuming you are linear. It says if you know it's linear, then you have to have t of 0 goes to 0. That's what A implies B. And so my antecedent says I need to have linearity already checked for this to work. What they're doing is we're going to do the contrapositive. I'm going to negate this statement and negate this statement. So this is logically equivalent to what you're going to use it for and why this is so important. The best way to show that a function or a transformation is not linear is showing 0 doesn't go to 0, because the contrapositive now says if t of 0n does not map to 0m, the negation of this equality, this implies that the negation of this statement, t is not linear. I really don't know why books don't point this out better, but this statement they state, and then they carry on with the rest of the discourse in the chapter or the section. They're assuming it's linear to use the theorem. That's not how you're ever going to use something. You're going to only ever use the statement to show something is not linear. To show it's linear, you have to run the two axioms. You have to. The analogy is, if I see or define mammals as warm-blooded, has hair, gives internal gestation, and what? Milk. Half of the species at least produces milk. And then there's non-placental mammals and placental mammals, and they've changed it and made it more complicated. I'm sticking with those 4 axioms. If I need those 4 things, I have to check them every time. But as we go, and I run around, I'm like, okay, and now they're like, get out there and be a biologist and figure out what these species are. So then I'm running around and I catch something, and I catch a lizard. I'm like, mammal? I could check axioms. I have to check cold-bloodedness. I don't even know how to check cold-bloodedness. Do you know how to check? I don't know what that means, or I don't know how to check it, but that's a hard axiom to check. And you're like, I don't know how to check some of these axioms. I know. I don't know how to check cold-bloodedness, but I can tell he's got no hair. He's got scales, so not a mammal. So check the easy ones. Why would I try to analyze and check and take him back to a lab and try to ruin his life and everything else by trying to find out whether he's cold-blooded? He's not a mammal because he doesn't have hair, and mammals need hair. So, why would I check the hard axioms? The point of that is, check the easy axiom. If it's not 0, then not linear. Never say, oh, 0 mapped to 0, therefore linear. No, I can give you nonlinear functions which go to 0. X squared goes map 0 to 0, not linear. So don't try to use the reverse. If it's linear, then 0 maps to 0, good. But what you really want is, if it's not 0, it's not linear. How do we use that? Example. Decide if each transformation is linear or not, I guess. I don't know why I need the parasitic part. I could have ended the statement there. If it's not, tell me. Yoda. Do or do not. There is no try. Law of excluded middles. There's only or not. There can't be a third option. So check if it's linear or not. Trichotomy, we did watch that video. Sometimes there is a choice of 3. But here, the law of excluded middles says, Yoda says, do or do not. There is no try. Saying I tried is just rearranging saying I didn't do it. I attempted and didn't. That's a did not. Trying is still a did not. Do or did not. There is no try. Thanks, Yoda. So, decide if each is a linear transformation. I should probably put some up there. 1. We're going to make them up. T, first of all, is going to go from R2 to R3. So we're going to go up a dimension. And what is it going to do? It's going to tell me that T of X, it says they're going to tell you, or if they're really nice, they should tell you that T of X is x1, x2. That's what an arbitrary guy in R2 is going to look like. And then it has to go to, where is it going to go? It has to be in here, so it has to have 3 coordinates. What I'm going to do is just draw this guy like this. We're just going to map them to identity and then blow him up by doing the sum of the 2 coordinates. There's a, is this linear or not? Yes, it is. How do I tell? I can tell because I'm a wizard. You tell by checking the 2 axioms. I should also call these A and B because my axioms are I and I. B. T is going to go from R2 down to R1, which is going to be, let's see if I can do this cleverly. Let's do this actually. R4 to R1, where it maps T of x1, x2, x3, x4 to x1, x4 minus x2, x3. That's determinant. Is he linear? I don't know. All right. That should be good enough. I'll do another one if it didn't work out to what I wanted. Let's throw another one in there. Let's do T from R2 to R2, the same dimension. So this one went up, this one went down, this one went straight across 2 dimensions. So this one's an operator on R2. And we're going to do T of x1, x2 equals 1, x2. Let's try these. Now I'm going to have to remember what the heck they were, so mental memory. I'm pretty sure, because I was a smart ass, that I remember what those are. Let's do the first one. As I go, you're going to see me do this every time. I have to take 2 things in here and add them, and I have to take 1 thing in here and scalar multiply it. I have to check the 2 axioms. First, the 3 things you should always check are in order now. Is T of 0 equal to 0? Now I'm not going to put the subscripts, but hopefully you know what I mean every time when they do that, or in the book they mean this is a different dimension, in 3 dimensions. If that's not true, you're done. You can say not linear. Why even check if it's warm-blooded or not? It didn't have hair. Done. Axiom done. If that is 0, you have to keep checking the other things and make sure that it has all the things to be, because you grab a platypus and you're like, oh, it's got hair. I'm done. No, he's lays eggs so close, but you got to check them all if you want it to truly be a mammal. What's the next thing I need to check? T of kx equals kt of x. They say spits out scalars, and then I have to take 2 things every time. T of x plus y has to equal t of x plus t of y. Remember, this is an R2 and this is an R3, adding an R2, adding an R3 of the images. We want to know if that is going to work. This is what I have to check every time. For 1, yes, T of 0, 0 equals, I literally just do what it said here. I put them where their selves are, and then I add them, and luckily 0 plus 0 is 0. So I get 0, 0, 0. T of 0 is 0. Check. I can't say therefore linear. I have to check the other things. Platypus has hair, but not mammal. Lays eggs. Check them all. They're cute. What's the only other one? The echidna. The echidna. Monotremes. This one, what does that look like? Every time I have to take that. Kx looks like this. Kx1, Kx2. That's Kx. I'm not even writing it out. Kx is this guy. So if I do that, T of Kx1, Kx2 is equal to, well, it says I have to do the first coordinate goes to the first coordinate, the second coordinate goes to the second coordinate, and then I add those coordinates. And then now here's what's hard, because you have to see now scalar multiplication in reverse. Is there a k in each coordinate? Yeah, let's clean it up and we say, just to make sure that you can see it a little bit better, I'm going to write this as k times x1, k times x2, and then I have k in both terms so I can factor it out. That's k times x1 plus x2. Do Do I have k in all three terms? Yeah, so I can write that as scalar multiplication. That is k times the vector x1, x2, x1 plus x2. What is that? That is k times, who's this guy? Our definition. This is t of x. That's hard at first. Rewind a couple times. Look, meditate on what that's saying. Yes, this guy is the original t of x. Now let's do it with 2. And we're done. So yes, this is also check. Scalar multiplication. It preserves this linear operation. It's almost a linear operator. Transformation. What's the third condition? X plus y is equal to x1, x2 plus y1, y2, which is equal to, coordinate-wise, x1 plus y1, x2 plus y2. You have to build that every single time. You should just start doing that for you. Build a sum, build a scalar multiplication. What do I have to do? 0 goes to 0. Scalars, it spits out. Sums, it splits. Let's see what happens. Now I do t of x plus y. Well, that's going to be t of this hot mess, which isn't so bad this time. x1 plus y1, x2 plus y2. Yes, when you see what's going on, this is like watching paint dry. It's just as boring. You have to go through the motions. Once you see what the axioms are, the game never changes. Check that 0 goes to 0. Check that it spits out scalars. Check that it splits sums. Now I do that. What did it say? Now I'm applying t. At this stage, I'm saying, what is t doing? It says put this wherever this was in the original function. So I'm going to put x plus y goes to x plus y1. x2 plus y2 goes to x2 plus y2. And then these two coordinates are going to get added in the last coordinate. So now defining what t does to this point, it sends it to a 3-space point, which is x1 plus y1, x2 plus y2, and then x1 plus y1 plus x2 plus y2. And then, yes, quite literally, using the correct term for literal, all I'm doing is associating all the brackets and grouping the x's together and the y's together, and then I want to see this reverse as sum. See, here's sum forwards. You're like, yeah, I get it. Coordinate-wise, can you see it in reverse is what I now have to do. Given this, can you see that that is x1, x2, I don't know what that was, plus y1, y2. That's what you have to see. Run the axioms in reverse. Once you have that, so what they do first is they're going to associate all the brackets and write that like this. x1, x2, x1 plus x2 plus y1 plus y2 plus y1 plus y2. They've grouped the y's and the x's together. Now can you see that that's the sum of two vectors in reverse? Yes. Plus y1, y2, y1 plus y2. And who's this? T of x. And who's this? Put a y in there and I'm going to get y. Y is what you ask because Mark said to. So it 0 maps to 0. It spits out scalars and it splits sums. T is definitely linear. Sentence fragment. T linear. No time for words. B. We had t from R4 to R1, which was t of x1, x2, x3, x4 equals x1 times x4 minus x2, x3. What's going to get ruined in this one? Something? Possibly. Only one thing fails, so we have to check them all. That dang platypus. Platypus! Cat, you've seen catfish. You just got platypied. You just got platypied. Patent pending, patent pending, patent pending. 1. Axiom 1. Even in a regular linear algebra video, what can you do? T of 0 is t of 0, 0, 0, 0. And that's going to be 0 times 0 minus 0 times 0, which is 0. 0 mapped to 0. Good. Therefore linear. No! Stop doing that. If it's linear, then it will do that. But not all. If you're nonlinear, it may do that also. 2. Scalar multiples. kx1 or kx is equal to what? Every frickin' time I have to do this. So this is kx1, kx2, kx3, kx4. And that is equal to, that implies when now I apply t to that, t of kx is equal to t of kx1, kx2, kx3, kx4. Yes, just go through the motions. And now I apply t to that thing. I put those wherever here. And it ruined two of the properties, didn't it? It pulls it out in scalars and squared, or to the power n. What's k times the determinant of a? K to the n. You gotta be careful. I said that wrong too. You can correct me. What am I gonna get? kx1 times kx4 minus kx2 times kx3, which is k squared times x1, x4 minus x2, x3, which is k squared times t of x, which does not equal k times t of x if k does not equal plus or minus 1. So it fails this. Never say, oh, 0 went to 0, therefore linear. Determinant is not a linear operator. It ruins scalars, and I'm not even going to really show. Once it fails, should I check to see whether the lizard's cold-blooded? Well, I don't know, but okay, I will this time. We got to take one just to make sure in the lab to verify. Don't just be like, I'm pretty sure he's warm-blooded. That's not how science works. But I think he was. No. Check. 3. T of x plus y. Every time, what's that look like? That's going to be x1 plus y1. I know you say it too, but this is what it is. Go through the motions. That now has to be x1 plus y1, x4 plus y4 minus x2 plus y2, x3 plus y3 does not equal. What do I have to have? x1, x4 minus x2, x3. You can flesh out the details, but this should be y1, y4 minus y2, y3, which would be t of x plus t of y. It doesn't equal that. Foil all of that out and you'll have extra terms is what will happen. And it's like, what is this extra term here? Because it's not linear. This is not linear. Determinant is not a linear operator, but it does send 0 to 0. Careful. Platypi. C. We have t is an operator now, and what it does is it does this. Every point in 2 space first of all, what is the operator again? It said I send you to 1x2. So I have an arbitrary point. Here's 1. Here's an arbitrary point, x1, x2 in R2, not the astromech droid, the plane R2. And what do we get from that? That tells us from this arbitrary point, x1, x2, it's sending me to the x1 value should be a 1. So also here, I should have drawn this to scale. Here's a 1. I got it wrong. I was going to try and project onto the wrong one. Good thing. So then what does that say? It makes the first coordinate a 1. And it's going to send me to that point, which is now the point 1, x2. That's where it's moving everybody. It moves everybody onto that line. That line is not through the origin, so 0 is not going to go to 0. Not linear. Done. I'll check some of the other axioms too, but that's the easy one. What do I check? 1. T of 0 is T of 0, 0, which gets sent to 0, 0, gets sent to 1, 0. So it didn't send it to itself. 0 should be a fixed point if you're an operator. But it sends me to 1, 0, which is not itself. So it's not a fixed point. So T is not linear. You're done. check the other two axioms for an exercise, or quickly I'll do scalar multiplication. T times kx is going to be what? T times kx1, kx2, yes, every time it's the same thing. And then what does that do though? It sends me to 1 kx2, which does not equal k times 1x2, which is equal to k times t of x. So the not means I couldn't pull a scalar out of this. I didn't have a k to take out of that one, so I can't. So not linear. Also, that you should meditate and rewind that one a little bit and spend some time on what that says. Is nobody likes this step that we do, so really slowly. This is what I get. And yes, I'm trying to train you at first to see that you need k in both, and then the other one you had to see that there was k in both terms and then take it out, and then it's scalar multiplication. I'm saying because I only have a k in this first term, I would need a k somehow to be in here, but I don't have it, and then I could take it out. So what I'm saying is that would be this here, but I don't have that, so it's not equal to that. And this is equal to kx1, and that's where I get a t of kx is not equal to kt of x. Arguing things are not true for everything is a lot harder than showing something works. Now let's show that every linear operator has a matrix, standard matrix associated to it, and every matrix can define a linear transformation. Okay, to finish off this video, what we're going to do is now show that every matrix, so let's tell the story. We're going to show that essentially mathematically in the big mumbo jumbo, what we're saying is every linear transformation can be viewed, has a standard matrix associated to it, so every linear transformation can be viewed as multiplying by a matrix for some matrix that we can find. And then if you have a matrix and you're multiplying it by vectors, you can define a linear operator or a linear transformation by just saying L of x equals a times x. So we can go both ways. Every matrix defines a linear transformation uniquely, and every linear transformation defines a matrix uniquely. So linear transformations are matrices, n by n matrices. They're the same thing. When you multiply matrices by vectors, it moves points around in n space to m space. When you take a linear transformation, it takes points in n space and moves them around in m space. They're doing the same thing as what this is about to get at. First of all, example. Let A equal 2, 3, 5, 7 be a 2 by 2 matrix. I'll stick to operator land when I can so that it's the Rn to Rn. What do I get from this? What I want to show is then we can define a linear transformation, basically the left-hand side of an n by n linear system, a times x. Linear transformation, t from R2 to R2. If it's m by n, it'll be Rm to Rm, as follows. This is what I was just saying in rhetoric. Now you can hopefully see it because of the power of algebra. If I take a point in n space, in 2 space, and I move it around with the transformation, that's the exact same thing as multiplying on the left by matrices. I just define it that way, where this is matrix multiplication. So for any matrix you have of any size, you have a transformation from Rn to Rm from that. In general, what are you going to have? If t goes from Rm to Rm, let's see if I got that backwards. I always do, but it doesn't really matter. I'm going to say that t of x, which is in Rn, is going to be the same thing as, now what do I need? X has to be n by 1, and so a has to be m by n. So the inside indices have to match, and the outside will be not x. It will be the image vector y, which will be m by 1. And that's what it's saying. For every matrix of any size, oh, I just did the reverse too. This is showing the reverse. If you have a linear operator, we're going to be able to find a matrix and show. That's what I'm going to do next. Stealing my own thunder. Give me that back, give me that back. What I'm saying here is, half of the theorem is saying, if you have a matrix, you can define a linear operator from that. Indeed, what is it going to look like? T of x1, x2 equals 2, 3, 5, 7 times x1, x2. This is 2 by 2. This is 2 by 1. The inside indices match, and the outcome will also be 2 by 1, which will be 2x1 plus 3x2, 5x1 plus 7x2. This is how Gauss sees matrix multiplication. Row I dot product column J is the ith entry of matrix multiplication. Good. Given a matrix, I can create a linear transformation from that by defining T in A. TA of x is A of x. Going the other direction, what will that say? The other direction will tell me, here's the clever trick that we're going to have to do. Given a linear transformation, how do I see that it has a matrix associated to it every time? I'll do an example and then I'll state the theorem that says it always works. So you can see it, I'm actually going to use the matrix I just used and do it in reverse because it is reversible. For every matrix I can create the transformation and it's unique. So if I give you the transformation, which was that I cooked up from just showing you, and I say how do we find the standard matrix from that? Well, the reverse of that sort of, and that's what I actually did when I was posed this. We're going to have a bigger theorem that says you can find it based on the images of the canonical standard basis vectors of Rn. What? Do this first. Example. T from R2 to R2 is defined as what we just did. T of x1, x2 is equal to 2x1 plus 3x2 and 5x1 plus 7x2. Now I just give it to you and it says here's a linear transformation. I have to view this as matrix multiplication. What I do is I do this. I'm going from R2 to R2. What that tells me is, what do I need? My matrix has to be 2 by 2. Why? I'm going to set it up like this. And what they're saying is this. I just would set up, the first time I was posed this is how I set it up. I'm trying to view this operation as this. And this is what we don't know. So what we do know is this. 2x1 plus 3x2 5x1 plus 7x2. We're given that, and I have to view that as this multiplication is what they're saying. What's that going to be? Well, to get this entry, it has to be this one times this, so I can reverse it. This will be a 2 and a 3 is what I need. Gives me this. And then reverse it. 5 and 7 is what I'm going to need. And then, so that says in our notation, the standard matrix of T is A, which is 2, 3, 5, 7. Given a linear transformation, I can always cleverly find a matrix associated to this. Linear transformations and matrices are essentially the same thing. Let's state that in the theorem and then we'll do a couple more examples. It's easiest to not do the if and only if. I'll do the statement and the converse statement in the same one instead of saying if and only if. What? Take some logic. Theorem. If A m by n is a matrix, then we can define what the part in here that we have to prove in the theorem part is. We have to actually prove that this T thing actually is a linear operator, and it is. Matrix multiplication, all this is satisfies this linearity conditions. Define a linear transformation TA of x equals AX. So I just showed you this. Obviously you do that. You just say T is multiplying by this. What you have to do in the theorem, what it's saying is that's actually a linear process. And it is. Conversely, so this is the direct statement. If you're a matrix, I can build a linear transformation from you. Conversely, which is not always true, but in this case it is, so it's an if and only if statement. If you're a linear transformation, I can find a standard matrix associated to you. If T from Rn to Rm is a linear transformation, we can find what we're going to call, I stick in the star, the definition in the theorem, standard matrix A, which we're going to denote as bracket T from A, or from T. Let me read that again. Conversely, if T is a linear operator from Rn to Rm, we can find a standard matrix associated to that such that basically it's the same as moving them around. So what they're saying is matrices and linear transformations are the same thing essentially. If I have a matrix, I can find a linear operator. If I have a linear operator or a linear transformation, I can find a matrix from this, which we're going to denote like this. Let's do that a couple times, and then we'll state one more theorem which tells us how to find this standard matrix systematically, which will be useful in the next video when we do the demographics. So in our examples A, let's do linear operator from R1 to R1. This is regular calculus, essentially, functions, but let's call him, you'll see, a linear function is not a linear operator. Let's call T of x equals ax plus b, where b is not 0. So the y-intercept is not 0. This is not a linear transformation. It is a linear function. I know they've used this homonym, synonyms, one of those guys. Not the same. They used the same word twice. Math, not English. What do I have to check? Is every time linear or nonlinear? I was supposed to be showing you the standard matrix of this, but we can't ever find one for this because I just thought I'd show you quickly before I do the real one. When you take that off, then it will be linear. They have to pass through the origin. 0 has to go to 0. So 1, is this linear even? Before you find the standard matrix also, this is why I cleverly did it. If they don't give you a linear transformation, you can't ever find a standard matrix. X squared has no standard matrix because he's not a linear function. X has a standard matrix. What are we going to do? 1, it fails us already. T of 0 is equal to a times 0 plus b, which is 0 plus b, which is b, which is not 0, so not linear. It failed. B. Now we'll do an actual linear one. The rest of them will be linear. From R to R now, let's do T of x equals ax. Any line to the origin, those types of guys are linear, and they will be a linear operator in the sense that we're talking about now. 1, T of 0 equals a times 0, which is 0 for any number, so check, it sends 0 to 0. 2, if I do T of kx, this is a times kx, which is a k, I can associate and commute everything. So associate the brackets technically, let's do them one at a time. I can associate that as a times k times x, technically is what we're doing. Then I commute them, which is, I know it's a whole lot more work than you thought. Then that will be k times a times x. And then that is kax, which is what? Kt of x. You didn't have to do all the associating steps, but that's technically what we're doing. Axiom. 3, T of x plus y is equal to a x plus y. And by another axiom of the vector spaces, I can scalar distribute that onto there, which is ax plus ay, which is what? T of x plus t of y. So linear. What's the standard matrix of it? A. It's a 1 by 1 matrix. This is weird, I know, I'm doing calculus functions. Let's move up in dimensions now. C. T of x is equal to, sometimes the book does this, so I'll be mean and do that to you. I know that this guy is in R3, and then they're mean, and they're going to say this is x1 plus x3, and this is x2 plus x3. So what they're saying, if they do that in the book, what they really mean is this. I don't know why they don't just do this. They're sending the 3-point to the 2-point, 2-dimensional vector. This is linear, you check. Exercise, this is definitely linear. How can you tell? If all of the coordinates of this is a linear equation in a and x, it's going to split out scalars and split sums. So this is linear. Anytime you have a constant term which is not 0, it's going to ruin it, just like the one I just showed you with the b. So this is linear. Find the standard matrix of this. Let's do it two ways, and then I'll show you preemptively what the theorem is going to say so that you can see what the theorem says, and then that'll be the end of the video. Mic drop. See you later. See you in the next one. What is the standard matrix? The way that I like to do it is, I know that it has to be a 2x3 matrix because it's reverse. So this has to be a 2x3 matrix. Why? You can get this straight in your head if you start drawing this game, and this is why I liked it at first. Matrix multiplied by, I need x1, x2, x3. They gave me what I have to multiply it by. I'm saying T is matrix multiplication. And that has to equal, and this is the information they gave me. They gave me this guy who is a 3x1, and that's how I know it has to be 2x3 because the inside indices match. And then I'm going to get a 2x1 vector, which is x1 plus x3, x2 plus x3. Which is 2x1. Inside indices match, the outcome will be the size of the outside indices. So that's what I set up for myself, and now this has to be viewed, this has to be matrix multiplication, which I know how to reverse anyways, and this is why I show you when we show what matrix multiplication is and everything else, where Gauss gets this from is viewing this as this type of scenario. And now what is that? Well, I need a 1 and a no x2s and an x3, and then I need a no x1s and a 1 and a 1. And then try it. x1, 0 x2s plus x3, yes. 0 x2, x3, that's exactly what we get. This says that the standard matrix of T is the matrix A, which is 1, 0, 1, 0, 1, 1. They like this because it says it's T is the operator technically. And this is the matrix associated to it, and we're saying they're the same thing. They're isomorphic, but they're not the same object. But if you don't care at all, there's the standard matrix of this operator T. Let's do it the other way, and then I'll show you what the theorem says. The theorem is going to say this. In R3, E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. In R3, and T of E1 is equal to T of 1, 0, 0, which is equal to, what do I get? 1 plus 0, 0 plus 0, which equals 1, 0. I'm just putting these values into here. And then T of E2 is equal to T of 0, 1, 0, which is equal to T of 0, 0, 0 plus 0, and 1 plus 0, which is 0, 1. And then T of E3 is equal to T of 0, 0, 1, which is equal to... All right, so once I have the image of these canonical basis vectors of R3, these are the standard canonical basis vectors of R3, E1, E2, E3. Once I see what their image is under TR, I get these vectors. What the theorem is going to tell me is that these columns as columns, this is the standard matrix. The standard matrix is always obtained by looking at the canonical basis vectors of your domain, applying T to those, and then I can describe everybody because they're a basis. I can tell where everybody goes. And so what does that say for us? This tells us because I got those, the standard matrix for T, they're going to say in the theorem, the bracket went on the wrong side. The standard matrix for T is equal to T of E1, they say, column T of E2, column T of E3. What the heck are they talking about? These are them. This is T of E1 and T of E2 and T of E3. And this is what they're saying. 1, 0, 0, 1, 1, 1. This is the standard matrix. And for more complicated linear transformations, or like when we start doing rotation and stuff like that, it's much easier to find the standard matrix by doing, we're going to find that rotation through counterclockwise through angle theta is going to be cos theta, negative sine theta, cos theta. It's like, how are you getting that? We're going to use trigonometry and look at what E1, 1, 0, and 0, 1 goes to in the plane, and then we're going to find and create cleverly the coordinates for the standard matrix. This is the image of T of E1 under a rotation, and this is the image of under where T of E2 goes under rotation. And that's what they're talking about. So, theorem, if T from Rn to Rm is linear, and A is the standard matrix of T, then A is equal to T of E1 column dot 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 column T of En, where EI is equal to 0 dot 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 0 1 0 dot 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 0, where he has a 1 in the ith spot, are the standard basis vectors of Rn. This is what the theorem is saying. Basically what it's saying is we have, for any linear transformation, we can find a standard matrix associated to it. That was the first theorem, and finding it isn't that bad anymore. What you have to do is it's unique. This standard matrix is uniquely determined up to what happens to the canonical basis vectors under T. Please subscribe below, and I will post many more videos on this series, and there's a bunch of other series if you want to look at these, but I'll see you next time.